Welcome back to Be Inspired from Life. Let's slow down and really sit with this idea. Most of what we call matter, your body, the air, this stage, the entire planet, is overwhelmingly made of space, not the calm, silent, empty kind of space you imagine when you close your eyes. The space inside matter is alive with activity, and once you see it clearly, the world never looks ordinary again. Picture an atom enlarged until its nucleus is the size of a marble. The nearest electron cloud wouldn't be just a few centimeters away. It would be somewhere out near a stadium wall. Everything in between, that's the nothing we're talking about. And yet, it's not really nothing at all. What fills that region isn't tiny hidden particles waiting to be discovered. It's a buzzing landscape of fields and probabilities. Electrons don't behave like miniature planets making tidy orbits. They behave more like possibilities smeared through space, like a whisper that could be anywhere until you listen for it. And the moment you try to pin one down, the universe pushes back, as if to say, you can know where it is or how fast it's going, but not both at once. Those aren't philosophical rules. They're experimental facts. Now, if all that space were genuinely empty, you might expect atoms to drift through one another like ghosts. But they don't, because the emptiness is threaded with forces. The negative charges of electrons repel other electrons. Quantum rules forbid certain particles from occupying the same state. These limits are not obstacles we complain about. They are the reason anything holds its shape. The space is actually structure, invisible scaffolding built from mathematics and fields. When two atoms get close, their electron clouds overlap and negotiate. They exchange energy, settle into turns, and form bonds. Chemistry, everything from salt dissolving in water to DNA copying itself, is simply the choreography of those patterns. That means the flavor of your food, the strength of steel, the sparkle of a diamond, the softness of skin, all of it emerges from interactions unfolding mostly in space. Not solid stuff colliding, but fields interacting, probabilities interfering, rule being obeyed with exquisite precision. And the deeper you look, the more surprising it becomes. Even in regions we call vacuum, energy flickers in brief ghost-like appearances. Particles pop in and out of existence so quickly we only detect their effects indirectly, yet those effects are measurable. Empty space, it turns out, participates. It shapes how particles move, how atoms form, and how light travels. Reality is less like a pile of bricks and more like a symphony. Notes appear, resonate and fade, guided by an unseen score. This understanding forces a beautiful shift in perspective. We grow up believing that solid means densely packed matter and that empty means nothing at all. But what holds your chair together? What stops your hand from sinking through the table? What let stars burn quietly for billions of years? None of that comes from solidity. It comes from relationships among things that are mostly separated by space. The universe builds stability not by stuffing everything full, but by arranging rules in the gaps. And there's something profoundly humbling about that. The world works not because nature filled every corner with material, but because the spaces in between are governed by principles so consistent, so subtle, that they create order out of almost nothing. When you realize this, the ordinary becomes extraordinary. You're not sitting on a simple chair, you're floating on a web of forces suspended by the quiet insistence of quantum law. What looks like emptiness is actually the stage on which everything meaningful happens and recognizing. That is the first step towards seeing reality as it truly is. Let's take the next step in the journey and ask something that sounds simple but turns out to be wonderfully strange. If matter is mostly space, why don't atoms just collapse into each other like cars piling up on an icy road? Why do they keep this respectful distance, as if there's an invisible rule that says this far and no farther? The answer isn't brute strength. It isn't tiny billiard balls banging around. It's a delicate balance of forces and quantum rules, and once you see it, you realize the universe is behaving with the precision of a master choreographer. Start with something familiar, electric charge. Electrons carry a negative charge, and negative charges repel one another. If you try to force two clouds of electrons together, they don't politely negotiate, they push back. This repulsion isn't optional, it's built into the very fabric of nature. The closer you try to bring atoms, the stronger that repulsion grows, like compressing a spring that stiffens the harder you squeeze. That force alone already explains part of the distance between atoms. It sets the stage, but it doesn't tell the whole story, because if that were all that was happening, you might still imagine good engineering could pack atoms tighter. Nature, however, added another rule, one that comes not from classical pushes and pulls, but from the quantum identity of the particles themselves. The electrons in atoms are not just little beads, they are quantum objects, and many of them are identical in a way that matters profoundly. There's a principle, one of those laws that's as mysterious as it is unavoidable, that says two electrons cannot occupy the exact same quantum state at the same time. It's like every electron carries a passport, and customs strictly refuses to stamp two passports with the same entry. This is the rule that keeps matter from collapsing into a single undifferentiated lump. It's not force in the usual sense, it's restriction. It's the universe saying you can't all sit in the same seat. When you press atoms together, you're not only fighting electrical repulsion, you're also trying to cram electrons into states that are already taken. To avoid breaking the rule, they must jump to higher energy states, and that costs energy. The result is resistance. Matter stiffens the more you try squeeze, the more the cost rises, until the effort becomes enormous. Without this rule, stars, planets, everything would collapse like a house with no beams. With it, structure becomes possible. Wood supports weight, water stays liquid, mountains stand quietly for millions of years. And yet, these same rules also allow atoms to bond and form the diversity of materials we see. At a certain distance, attraction and repulsion reach a balance. Electrons share space in carefully arranged patterns, obeying the laws while still interacting. That balance is chemistry. Entire tables of elements, the way metals shine, why glass is transparent and salt is brittle, all of it is the byproduct of atoms respecting both the electric push and the quantum prohibition. What fascinates me is that respect isn't conscious. It's mathematics expressed as behavior. You press your hand on a wall and stop, not because anything truly touches, but because the electrons in your hand refuse to inhabit the same states as the electrons in the wall. The experience of solidity, the feeling that the world is firm and reliable, is really the sensation of being denied access by rules deeper than intuition. And here's the inspiring twist. Out of limits comes possibility. The universe does not build stability by brute force, it builds it by constraints. The very laws that say no are the same laws that make everything we love and recognize possible. When you realize that atoms keep their distance not by accident, but because nature is quietly enforcing order, in the smallest spaces, you start to see that what looks ordinary is actually miraculous, and that our world stands, quite literally, on the strength of invisible rules. Now let's clear up one of the most persistent pictures our brains love to cling to, the idea that electrons are tiny planets circling a tiny sun. It's a great mental cartoon for children, and completely wrong for grown-up physics. If you imagine electrons whizzing around little circular racetracks, you miss the most astonishing part of the story. Electrons don't orbit in the classical sense. They exist as clouds, fuzzy regions where there's a certain chance of finding them, and that single shift in perspective changes everything about how we understand matter. Think for a moment about why the planet idea is so tempting. We like objects that have ions and speeds and paths. You throw a ball, you can predict where it's going to land. That kind of thinking is baked into our nervous system. But inside atoms, nature refuses to play by those rules. If you try to imagine following one electron frame by frame, asking, where is it right now? The universe shrugs. The best answer we can give is a probability, not because we're lazy or the microscope. Pairs aren't powerful enough. It's because reality at that scale simply does not have a precise location to offer you until you measure it. So we describe electrons as waves of possibility. They form standing patterns around the nucleus, like musical notes sustained on an invisible instrument. Each pattern corresponds to an energy level, not a track the electron runs around, but a shape of probability it inhabits. When an atom emits light, the electron isn't leaping across space like a frog jumping lily pads. The entire probability pattern changes, and energy is released in the process. It's more like the whole atom retunes itself. That's weird. It should feel weird. And yet it predicts experiments perfectly. If electrons were little planets, atoms would be unstable. They'd radiate energy, constantly spiraling into the nucleus. The universe would collapse into a featureless smear. Instead, quantum mechanics says electrons occupy allowed states, and only those states. They don't spiral in because there's nowhere lower to go unless the rules permit it. Stability comes not from motion, but from mathematics. Now here's the part that's easy to miss. This fuzziness is not sloppiness. It produces precision so sharp that our best measurements agree with theory to astonishing digits. The cloud picture explains why atoms have sizes, why elements behave differently, why metals conduct, why semiconductors make computers possible. Those probabilities dancing quietly around nuclei are the architects of technology, biology, chemistry, everything complicated and interesting. And not something else. The cloud is not just spread out in space, it can interfere with itself like a wave. Put two atoms close together and their clouds overlap, combine, and create entirely new shapes. Those shapes decide whether atoms bond tightly, loosely, or not at all. So what feels like the solidity of the world is really a story about patterns in probability weaving together. You might wonder, if electrons don't have definite orbits, what happens when we measure them? Suddenly we get a definite spot. It's as if the universe waits until the question is asked, then commits to an answer. But the moment the measurement ends, the electron again spreads into a cloud of possibilities. That's not a trick. That's nature being honest about how it operates at its deepest level. This idea force, a kind of intellectual humility. Our everyday intuition, so trustworthy for cars and baseballs, is hopelessly out of its depth inside atoms. And yet, instead of despairing, we can marvel. The world is not less real because it is probabilistic. It is more mysterious, more subtle, and in a strange way more elegant. We discover that certainty is not the foundation of reality. Pattern is. So, patchwork. You imagine the inside of matter. Don't picture tiny planets racing around. Picture shimmering clouds, overlapping, interfering, obeying rules that seem alien and yet build everything familiar. In that shimmering lies the proof that the universe can be both unpredictable in detail and utterly reliable in outcome. And that is where the real wonder begins. We've been talking about electrons as clouds of possibility, arranged in patterns around the nucleus, and now comes the rule that quietly prevents the entire universe from collapsing into a dense, featureless lump. It's not a dramatic explosion or a mighty force. It's simply a principle that says some particles just won't share. Two electrons cannot occupy the exact same quantum state at the same time. That's it. Modest sentence. Immense consequences. Imagine a theater where every seat is unique. Different angle, different view, different cushion. Now imagine every electron arriving with a ticket that only fits one particular seat. If the seat's taken, it has to find another. Higher up, further out, at a different energy. You can pack the theater, but you cannot double book a seat. This isn't etiquette, it's law, and because of this law, electrons stack themselves into layers, filling the lowest energy states first, then the next, and the next. Atoms get personalities, elements are born. The periodic table isn't a helpful chart on a classroom wall. It's the visible fingerprint of this rule written across matter. Think about what would happen without it. Electrons would all slide into the lowest state available, outing into the same place. Atoms would shrink to almost nothing, their electrons huddled right on top of the nucleus. Chemistry would vanish. There would be no structure, no subtlety, no difference between carbon and gold, between oxygen and neon. The universe would be as exciting as a brick with no internal design. Instead, this simple restriction forces order. It makes the world layered, varied, and astonishingly rich. This principle also explains why matter resists compression in ways that feel almost magical. When you squeeze something, a metal rod, a piece of wood, even your own body, you're not bumping objects together like marbles. You're trying to shove electrons into quantum states that are already occupied. They refuse. So the system responds by pushing back. To pack things tighter, you'd have to lift electrons into higher and higher energy levels, and that energy cost grows rapidly. It's like stacking luggage in a plane. Once the overhead bins fill, you don't just cram another bag into the same space. You have to store it somewhere increasingly inconvenient. On cosmic scales, this same rule holds white dwarf stars up against gravity itself. Whole suns collapse when they run out of fuel, the core falls inward, and then, incredibly, it stops. Not because anything is pushing outward in the usual sense, but because the electrons will not be forced into identical states. That quiet refusal becomes a pressure strong enough to support a star. One abstract quantum restriction, holding up a stellar corpse the size of Earth. If that doesn't give you goosebumps, check your pulse. And back here on Earth, the same principle shapes every familiar object. It's responsible for the stiffness of solids, the structure of crystals, the way metals conduct electricity but not too freely. It determines how atoms line up, how bonds form, and how matter keeps its shape. The tables we rest our arms on, the floors that don't give way, all of them are really negotiations conned, acted by electrons following a rule that never wavers. What I love most is that this is not a force shouting stop. It's a quiet rule whispering you can't be identical. Out of that whisper arises resistance, architecture, and stability, a universe with more possibilities, precisely because some possibilities are forbidden. So the next time you lean against a wall or stand on the ground, remember, you are being supported not by solidity, but by a principle of exclusion that organizes the microscopic world into layers of enduring structure. In a universe that often feels chaotic, it's a reminder that order can emerge not from power, but from limits, and those limits are the reason anything at all can stand. We've been circling around this strange idea that the world looks solid, feels solid, behaves solid, and yet underneath there is almost nothing there except rules, fields, and a lot of empty space. Now let's lean into the illusion itself. When you set your hand on a table, you swear you're touching wood. You feel firmness, resistance, a clear boundary between you and the table. But at the level of atoms, nothing actually touches. What you're feeling is a conversation between fields, and that conversation is saying, quite firmly, no further. Each atom in your hand carries electrons, wrapped in those fuzzy probability clouds. The table's atoms do too. Those atoms approach. The negative charges around them begin to interact. Electromagnetic forces rise sharply, like an invisible wall thickening in front of you. At the same time, the quantum rule that forbids electrons from sharing identical states kicks in. To move closer, the electrons would have to be squeezed into configurations that cost enormous energy. So the fields push back, not politely, relentlessly. Your nervous system interprets that pushback as pressure. Your brain translates it into the sensation we call solid. But no two atoms ever physically bump like billiard balls. They hover, repel, led by fields and restricted by quantum law. The hardness of the table is simply the amount of energy required to distort those fields and break their comfortable arrangements. That's why rubber bends and steel doesn't. You're not testing muscles in the material. You're testing how easily its atoms can be coaxed into slightly new patterns without breaking the rules. Think about walking across a floor. Gravity is pulling you down, trying to accelerate you toward Earth's center, yet you don't fall through. The atoms in the floor rearrange just enough to create an equal and opposite electromagnetic response. The floor pushes up not because it wants to, but because it cannot allow its electrons and yours to occupy the same quantum states. Newton's equal and opposite is really quantum me. Channik's wearing a classical disguise. Even the idea of weight feels different once you see it this way. Your weight isn't some mystical property inherent to your body. It's the measure of how strongly the earth must push back to keep you from sinking. You are constantly being supported by fields that refuse to overlap more than physics allows. Every step is a negotiation with the vacuum between atoms, and the vacuum wins. What's beautiful is how universal this explanation becomes. The strength of metal girders, the flexibility of plastic, the bounce of a basketball, the crisp snap when a pencil breaks, all of them are variations on how fields deform and resist. At small strains, the fields stretch like springs. Push harder and they rearrange. Push too hard and the patterns fail, bonds reorganize, and the material cracks. It's not that matter is stubborn, it's that the rules are. Once this clicks, touch itself feels like a magic trick. The atoms in your fingertip never mingle with the atoms of anything you press. The closest they get is a narrow gulf where forces roar loudly enough to stop motion. The world is held together by unseen interactions that do their work so flawlessly we mistake them for substance. But there are no tiny girders under the surface, no microscopic concrete. There are only fields guided by laws that never blink. And that turns out to be far more inspiring than the simple idea of hard stuff packed tightly together. It means solidity is not an accident. It's a promise kept by nature at every moment, everywhere, without fail. It means reliability emerges from invisibility. It means the firmness we trust with our lives is really the quiet insistence of physics echoing through space. So the next time you slam a door, tap a glass, rest your head on a pillow, remember, nothing is truly touching anything else. You are suspended. Your entire world is suspended on layers of invisible resistance shaped by rules written into the universe long before there were eyes to see them. And recognizing that doesn't make the world less real. It reveals that its strength comes from something deeper than touch. By now we've peeked inside atoms and seen that what looks empty is actually full of rules and relationships. But there's one more twist that really stretches the imagination. Even in the places where there are no atoms at all, no electrons, no nuclei, no particles of any kind, the universe refuses to be quiet. What we casually call empty space is not the still silence of nothingness. It is a restless stage where tiny fluctuations flicker in and out, too quick for our senses, but crucial to how reality behaves. Picture turning off every light, removing every atom, every speck of dust, every photon of light itself. You'd think what remains is absolute nothing. Yet quantum physics tells us that even there, the fields that fill space, the ones responsible for particles and forces, can't sit perfectly still. They jitter, they vibrate. They produce pairs of particles and antiparticles that appear for a breath of time and then annihilate one another, vanishing back into the background. They leave behind tiny footprints, not in the form of debris, but in the way they subtly nudge the world. We don't see these ghost-like events directly the way we see raindrops or sparks, but we measure their consequences. They shift the energy levels of atoms just enough that our equations must include them to match experiment. They influence how light travels across space, how forces behave at short distances, even how the universe itself expands on the largest scales. The quietest possible vacuum is still humming. That's unsettling at first. We like to think of nothing as truly nothing. If a shelf is empty, it's empty. If a jar contains no marbles, we call it void. Quantum reality laughs at that simplicity. The vacuum is like the surface of the ocean seen from far above. It looks flat and calm. Zoom in, and you discover ripples everywhere. They're small, but they never disappear. And this restless background doesn't just sit there as scenery. It participates. When two particles interact, the vacuum between them contributes. When atoms bond, the vacuum plays a supporting role. Even the forces that keep matter stable are shaped by this energy bubbling underneath. It's as if the universe never fully shuts down. The machinery keeps idling even when the shop is closed. One of the most mind-bending consequences is that the vacuum has energy, real, measurable energy, built into it. Not energy you could scoop up in a bucket, but energy that influences gravity and the shape of cosmic history. The idea that nothing could weigh something, that emptiness itself could push galaxies apart over billions of years, feels like a joke nature plays on our intuition. Yet the data point in that direction. The emptiness between atoms, the emptiness between stars is doing work, and this ties beautifully back to everything else we've explored. Atoms don't collapse because of quantum rules. Matter feels solid because of fields refusing to overlap. Electrons live as clouds of probability. All of that happens inside a universe whose baseline state is not zero, but a restless, creative almost something. The spaces in between aren't empty gaps in a structure. They are part of the structure. Remove them, and the story of reality falls apart. There's a philosophical temptation to say, well, if even nothing is something, then we haven't learned anything at all. But that misses the real lesson. The lesson is that nature is under no obligation to match our words. Empty, solid, touch, space. They're conveniences. The universe is subtler than our language, and the closer we look, the more it rewards us with wonder instead of certainty. So, when you imagine the space between atoms, that vast, invisible gulf, don't see a dead void. See a vibrant arena where the quietest fluctuations shape everything we see. Realize that even when the universe seems empty, it is busy writing the rules that make stars burn, molecules form, and life think about all this in the first place. And understand, with a mixture of humility and awe, that greatest surprises are often hiding in what we once mistook for nothing. Thank you so much for watching. If this video inspired you, be sure to like, share, and subscribe to be inspired from life for more motivational content. And remember, no matter where you are in life, you have the power to change your future. See you in the next video.